V basically represents how fast something is moving. But actually, frequency also kind of represents how fast things are moving. One of them represents how fast the oscillations are oscillating, and one of them represents how fast the wave is propagating. So let's try to clarify that. Is this the speed of propagation or the speed of oscillation?
I think it's propagation.
That's right. This is how fast the wave is moving, say how fast the wave is moving towards the wall. And then F would tell you how fast the oscillations are moving. Remember that this would be in cycles per second. So it would be telling you us how many cycles of oscillation we go through per second. Where this actually tells us is in meters per second. It tells us how many meters that wave actually propagates. That's a good way to think about the distinction between them. Okay. Any questions about that stuff?
So and then omega is angular acceleration, or is it angular? I can't remember.
Omega would
velocity.
be. That's right. So omega is confusing because you used it for something different a couple weeks ago in the course.
Yeah.
A couple weeks ago in the course, you were looking at rotation, and then you used omega for the angular velocity. The angular velocity. Now we're using omega for the angular frequency.
Angular frequency.
Right. And it's not a dumb thing that the physicists do that, because actually angular velocity and angular frequency are very analogous concepts. So it's actually a good idea to use the same symbol for both of them. But in this context, we would want to call it not the angular velocity, but the angular frequency. So we've got the regular frequency, and we have the angular frequency.
What exactly is angular frequency?
That's a good question. Now, that's also something I talked about a little bit in that other series of videos. I don't know if you got that far. It's basically another way of measuring the frequency. It's another way of measuring how fast you're oscillating with it. That's a good question. So let's take a look at that. I tried to emphasize in the other series, all of these concepts make more sense if you remember the units. I was just mentioning a second ago, do you remember what are the units for F? What are the units for the regular frequency?
I've been getting them confused all day. I want to say cycles per second.
Yeah, that's right. You got it. Do you get to use a cheat sheet for your course? Okay, so it should be a good thing to put in your cheat sheet. However, there's some things that are so important in the course that they're worth memorizing. You don't always have to look those up. Unless you know what these units are, you can't really have an idea in your mind of what the frequency means. Remember we were saying that the frequency tells us how fast the oscillations are. So these units should make sense. They tell us, say, how many cycles of oscillation we can go through per second. This is a little bit complicated because cycles is a kind of disappearing unit. Oftentimes this will just be written as 1/second. People don't always say cycles. I like to put it in though because it makes more sense. And there's a name for this, hertz, that you should also know.
Okay.
Now, omega is the angular frequency. Very important concept that again you're going to use for the rest of the course. And it's just a different way of measuring how fast the oscillations are moving, except now the units won't be cycles per second. We're not going to measure how fast we're moving in cycles. Well, how do we normally measure an angle?
Radians.
That's right. Actually, earlier in the course, we actually used degrees, but here you're right, we're going to use radians. So the units here would be radians per second. Again, sometimes people just say 1/seconds, but then we can get these two things confused. So maybe it's best to say this is in radians per second. Now, this is a little bit weird because these are kind of like pretend radians because we're not actually making an angle. What we're going to do here is we're going to pretend that the oscillation is going through a cycle, and we're going to pretend that we're going to pretend that a cycle is a circle. If you pretend that a cycle is a circle, then you can think in terms of radians. So the key is, how many radians are there in a circle?
I think 2 pi radians.
That's right, it's like 360 degrees. 2 pi radians in one circle. So how many radians in a cycle? Well, we're going to pretend that a cycle is a circle. So.
Okay. Which kind of, that's sort of the idea. I remember there was a drawing in class today where, like, a crest of a wave is sort of a half circle.
Right.
Right. Okay.
Yeah, exactly. So If the wave goes through one cycle, we could also say it's gone through 2 pi radians. And again, this is weird because they're just pretend radians. Nothing's actually moved in a circle, but if it were going in a circle, it would have gone through 2 pi. Or suppose that we've only gone through half a cycle. Well, if we've gone through half a cycle, we could pretend that's like pi radians. So there's 2 pi radians in the cycle. Well, let's say then that we're going through 3 cycles per second. Let's say the ordinary frequency is 3 cycles per second. What would the angular frequency be? If we're going in 3 cycles per second, how many radians would we go through per second?
6 pi?
That's right. You don't need any formulas for that. All we need is this basic idea. If 3 cycles is pretend like 3 circles, that would be like 6 pi radians per second. Or one more example. If omega is pi radians per second, in 1 second we go through pi radians, well, how many cycles are we going through per second?
Half of a cycle?
Yeah, that's right. That was a little bit harder. But a full circle would be 2 pi, so this is half of a cycle. So now the frequency we could say is half, or 0.5 hertz, 0.5 cycles per second. So if we just keep this in mind, it's easy to go back and forth between omega and f. Or you can just write down in your cheat sheet that omega is 2 pi f. If you think about it, this is the equation we were just using here. 3 times 2 pi is 6 pi. Or 1/2 times 2 is pi. But in a sense, if you really understand this idea, you don't even need this formula. It's just obvious how to go back and forth between f and omega.
Yeah.
The mistake that people tend to make, or I tend to make, is if I'm in a hurry, I tend to put the 2 pi on the wrong side. So it is a good idea to put it in your cheat sheet so you know that the 2 pi is multiplying times the f and not the omega. You saw how that worked out here. And this kind of takes us back to you were asking, so what does the angular frequency tell you? Well, it's just a different way of measuring the regular frequency. It's just a different way of measuring the regular frequency, but instead of saying how many cycles we go through per second, we imagine that a cycle is like a circle and then ask how many radians we're going through per second. It just turns out that some formulas are simpler or more convenient if you use these units instead of these units. So it's helpful to have both of these ways to measure this.
Okay.
These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you.